Hi everyone, I am Dr. Adil Majeed. I am currently working as a DST Inspire faculty in Department of Chemistry, NIT Srinagar. I have been recently awarded with Prime Minister Educator Research Grant from ANRF. I am highly grateful to ANRF for providing me this support for carrying out my research at NIT Srinagar. At the same time, I am also grateful to DST Inspire for providing me the opportunity to carry out my research as a DST Inspire faculty. Today I am recording my seminar on my research work, which is functional and responsive liquid repellent interfaces, which has wide variety of applications for water remediation, biomedical and energy related applications. So this is the overall research view of my research which I have done over the years. I have mostly worked on the lotus leaf inspired super hydrophobic surfaces, which has various applications for oil water separation, self-cleaning surfaces to anti-icing applications. I have also worked on designing functional and responsive slippery liquid interfaces for biomedical application and energy related applications. I have also worked on designing oil repellent surfaces and which has multifunctional applications. So today I'm going to discuss in brief about these different surfaces and their prospective applications. So in order to understand these liquid repellent surfaces, I would like to give a basic introduction of this field. So when we put a liquid droplet on a smooth interface, it has the three-phase interface, that is liquid vapor, liquid solid and solid vapor interface, and the point of contact of these three interfaces we called as contact angle, and this was first observed by Young's, which we called as through this Young's equation. However, when the surface has some roughness on the surface, the contact angle on those surfaces is explained by Wenzel model, which explains that increasing the roughness on the surface, for the hydrophilic surface, the surface becomes more hydrophilic, and for hydrophobic surfaces, the surface becomes more hydrophobic with increasing the roughness factor. However, when the contact angle is very high, above 150 degree, as like we see in the lotus leaf, the another model which we call as Casey-Baxter model explains very high contact angle. In this model, the liquid droplet is hanging over this texture because of this trap air which is in between these texture surfaces, and when this droplet on the surface is the water droplet, we call those surfaces as super hydrophobic surfaces. So these surfaces were inspired from the lotus leaf, and these surfaces are characterized as when the contact angle is greater than 150 degree and the roll off angle less than 10 degree, as we see in the lotus leaf. Those kind of surfaces are called super hydrophobic surfaces, and these surfaces are inspired from the lotus leaf, as we see under the scanning electron microscope. The lotus leaf has the bumpy structures, and those bumpy structures are further decorated with wax nano coatings, and which eventually gives the super hydrophobic property to the lotus leaf. And then these surfaces were artificially designed in order to get the super hydrophobic surface in the artificial means. The two criteria which need to be fulfilled. One is the dual degree of roughness, that is the combination of micro and nano texture, and the essential low surface energy coating. The combination of these two criteria gives the super hydrophobic surfaces. In the past, we have designed some super hydrophobic surfaces using polymeric nano composite materials. And we can see when we designed this gel, it became super hydrophobic by appropriate combination of hierarchical texture and low surface energy coatings, and these surfaces were further used for different applications, and we have optimized the different solvent conditions, and we found that the appropriate combination of texture and surface energy gives the super hydrophobic property. And these surfaces were further explored for water remediation, and as a stretchable membrane, we can see the super hydrophobic property remains intact even after 150% stretching, and that was further used for oil water separation. As we can see in this video, when we expose our super hydrophobic membrane to oil and water mixture, only the oil phase passes through and the water phase remains on the top of the membrane because of its super hydrophobic and super oleophilic nature. And this strategy was further extended to other substrates like cotton, and all these different substrates were super hydrophobic, and this cotton was further explored for separating the bulk oil which is present in under the water. And you can see that the super hydrophobic cotton selectively absorbs the oil phase while retaining the water phase there. However, this untreated cotton only absorbs the water. However, these super hydrophobic surfaces are unable to repel the low surface tension liquids. In order to repel the low surface tension liquids, another property is introduced, that is super oleophobic surfaces, which repels both water as well as other organic liquids or low surface tension liquids. So here we have designed the multifunctional super omniphobic surfaces which repels both water and other low surface tension liquids, but at the same time it shows the another functionality. Here in this case it is photochromic, which changes color in presence of light. So here we can see this surface becomes super omniphobic while when we expose it to the UV light, it becomes it changes its color but retains its super oleophobic property. And when we extend this method to the other stretchable or the fibrous substrate, it shows the similar property. However, here we want to demonstrate that why this super omniphobic property is important for color morphing materials. As we can see here that that when we expose the photochromic materials, one with super omniphobicity and another without super omniphobicity, here we can see the surface which is not super omniphobic compromise its color, whereas the surface which is super omniphobic retains its color morphing property. So which shows that this super omniphobic property helps in preventing the color morphing property in presence of different harsh organic or aqueous liquids. In addition to that, we have also designed the liquid crystal based super omniphobic surfaces, which has the reversible metamorphic property. That means it changes its shape in presence of heat, but at the same time it is super omniphobic in nature. Here we can see this liquid crystal elastomeric based super omniphobic surfaces repels both water as well as the low surface tension liquid, which is hexadecane. And this surface can be used for the microfluidic applications, while we can use these surfaces for mixing the two liquid droplets without any external without using any hand or using any external device. It simultaneously mixes two liquid droplets, as we can see here. So this particular material can be used as a stimuli responsive surfaces for microfluidic applications. However, in the broader context, if we see the fabrication of super omniphobic surfaces needs the presence of fluorinated carbons, and it has been substantially known, it has been well known that these fluorinated chemicals are environmentally unfriendly because they have the bioaccumulative nature and are harmful for both now for different and are responsible for various diseases in the human life. So it has, and moreover, this has been banned, these fluorinated chemicals has been banned in different places in the over the years. So here our strategy is to design this liquid repellent coatings without using the fluorinated chemicals or the fluorinated carbons. So in order to design that fluorinated, the super omniphobic or the liquid repellent surfaces without the fluorinated chemicals, so which shows that there is a significant need for designing this environment friendly liquid repellent coatings without using the fluorinated chemicals. So this is our hypothesis and this is our strategy to design the fluorine-free super repellent surfaces, and this is our hypothesis where we can design the fluorinated the super omniphobic surfaces without using the fluorinated chemicals, and these are our different aims and objectives while carrying out this particular research. And here particularly we are using the long chain hydrocarbon, which is a very long chain hydrocarbon, and in addition to that we will also be using other hydrocarbon in addition to that. So the mixture of that two in appropriate combination after different optimization steps, we aim to design that liquid repellent surfaces without using the extensive use of fluorinated chemicals. So the alternate strategies for designing these surfaces is like changing the solvent conditions, changing the reaction conditions, as well as the changing the reaction mediums. We aim to be designing these liquid repellent surfaces without using the fluorinated chemicals, which are bioaccumulative and environmentally unfriendly. So this strategy aims to design these liquid repellent surfaces without using fluorinated chemicals, and it will have different advantages like they are scientific advancement and biocompatible as well as cheap. They will be reducing the use of hazardous chemical materials, and which makes it sustainable and environmentally friendly approach. So with that, I would like to thank you again to ANRF for providing me the Prime Minister Early Career Research grant to carrying out this research. Thank you so much, and I would be happy to take any questions